All right, so welcome everyone to the 2023 Rockwood Memorial Lecture of the Institute of Neuroinformatics. So this has been a long-standing tradition, and we have had many distinguished speakers. We're very delighted today to have with us Tobi Delbruck from Zürich. So before getting started, a brief introduction here. So the Rockwood Memorial Lecture is in honor of Paul Rockwood, who unfortunately died in mountaineering accident. He was an early pioneer in language and speech technology in the days before you didn't hear about all this language modeling or AI for the matter. So this is made in request of by his family in honor to let this endeavor of machine learning / translation, machine translation, and more generally neural computation live on. And so, today, Tobi Delbruck comes from the lineage of neuromorphic engineering. In fact, he was there at the very beginning of the founding of the field in Cauwenberghs' lab many years ago. He has led a group in Zürich for many years. And so I would say he has really done remarkable work in what is now called dynamic vision sensing, but which is really has made a really lasting impact in the field of vision sensing. And it's all neuromorphic engineering. So he will tell us today, he'll give us a history of the field and some other exciting demos, and then we'll actually go on the whiteboard, because this is also co-located with a class on neuromorphic integrated bioelectronics. And Tobi is delighted to go on the whiteboard and share some insights on the actual circuits that go behind the magic that he'll tell us about. And so with that, so Tobi, please go ahead.
Okay, thanks. You guys in the back can hear me okay? Okay, first of all, I want to say that I'm very happy to take part in the Christmas apéro at the INC.
Inc.
The Inc, yeah, at the Inc, yeah. And the wonderful speech that Terry gave and various other people confessed their biggest mistakes and best decisions and things like that. That was wonderful. And I'm also happy to be back here again. And the way we're going to do this today is I'd like to tell some history, mostly history actually. It's quite interesting history, at least for me, and I hope I can convey the history of this silicon retina development, which goes hand in hand with the development of these cameras that you all have in your pocket. In each of your pocket, you have tens of millions of very good pixels. In fact, some of the phones have 4 or 5 cameras on them now. And that didn't exist when we started. In fact, when we started all this neuromorphic engineering stuff, people were still using CCD cameras, charge coupled device, and they were even using Vidicon tubes. The broadcast companies were using Vidicon tubes. This is actually a device where the photon hits a tube and then a high electric field accelerates the electrons and hit another plate, and then you would scan out the charge from that plate. And this didn't exist. And it was right when we were starting to do the very first silicon retina design at Caltech, Masher and Carver, as I'm going to show you. Eric Fossum, who you're also going to see here, was doing the very first CMOS image sensor design with an active amplifier in each pixel at GPL. And so this all kind of went together. And now like this is mass production technology, and it has many beautiful benefits for society and, of course, for social interaction. But it also has some drawbacks. But I'll tell you about that. So I'm going to tell you quite a lot of history. Then I'll give you a demo of a kind of a contemporary event camera. That's also quite fun. And then everybody who's not a circuit designer is welcome to leave. We'll take a little break, and then I'll do a little tutorial about this pixel design on the whiteboard. So I hope you enjoy this. And please interrupt me for any questions of clarification. Yes, Terry.
What are people looking at? They're looking up.
At a drone. They're looking at Benny's drone. Yeah, Benny's actually flying his drone. You see he's holding his drone controller here? Yeah, they're all looking up to see if it'll crash. Because at that time when this picture was taken, maybe 3 or 4 years ago, of the Institute, this is kind of novel stuff. That somebody had a drone and could take pictures with it. Nowadays, routine, right? Okay, so let's begin at the beginning. And I just want to ask you, does anybody recognize this picture? Anybody in the room? Yeah, this is probably the world's first or most famous early movie camera.
Yes.
Do you know, this is
So
actually,
this is, what's the guy's name?
you'll see.
Okay.
Yeah, this is a movie camera. This is 40 cameras, each of which take one picture, and the pictures are triggered, you know, when something breaks a thread here. Now, do you know what I'm talking about?
Of course.
Exactly. This camera resulted in the most famous first movie, The Horse in Motion. How many people heard of that? Maybe 40% of the room. Yeah, so this was a study that was commissioned actually by Stanford. The same Stanford, the industrialist and robber baron who funded Stanford University, actually his wife started Stanford University. And the technology for doing this to determine ostensibly if the horse actually was in the air when it was galloping. If you freeze it here, you'll see that the feet are all in the air at one time. You know, it didn't exist at that time. They could take still pictures, but not movies. And so this video is actually 150 years old. And since that time, the atom of machine vision has been the pixel and the molecule has been the frame. It's just a given that if you're going to do machine vision, you work with these sequence of pictures, right? And that's the way all computer vision people think. And, you know, now as you have in your phone, you have lots of really beautiful camera chips with very tiny pixels. They seem to work very well, but if you think about them, they have some drawbacks and they don't work like our eye at all. Because they keep sampling the same thing over and over again. And every pixel has the same exposure time. So, you know, if it's too bright or too dark, they clip against the rail. And of course, the output is very redundant. Incidentally, this approach to doing machine vision leads to the fact that frame cameras, what we call frame cameras, have this fundamental latency versus power trade-off. Has anybody heard of this? So if you want to do machine vision and you need to achieve a certain latency, a certain reaction time, you have to run at a high enough frame rate, right? Otherwise, you might miss what's happening and it takes too long to react. And you can do that as long as you're willing to burn arbitrarily high power, you can achieve arbitrarily low latency, as long as you have enough light, you know, to expose the picture. Or you can burn very little power by going at very low frame rate, but then you give up latency. And is that true for biology? Does it have a frame? Is it necessary that we do it that way? It's not necessary, actually, it turns out. But you know, if you're going to use frame cameras, you're going to face this fundamental trade-off. Now, before I leave this picture from Muybridge, I want to tell you a little bit about Muybridge because it's such an entertaining story. How many people know the story of O.J. Simpson? Who did not hear of the O.J. Simpson murder trial in LA? How many people did not hear of O.J. Simpson? Yeah, that was like the crime of the century here in Los Angeles, at least. Yeah, Muybridge was the crime of the century 150 years ago. He actually murdered, he went up and shot in cold blood his wife's lover at a holiday camp. Just walked up to him and shot him in the head, murdered him. And then Stanford actually paid for his legal representation and he got off on grounds of temporary insanity. So he's not a good man, you know. And it's very interesting. He first came to the States as a dealer in rare books. And while crossing the US, he had a stagecoach, he was involved in a stagecoach accident. He had a brain injury from that. That changed his personality. And then he went into this photography. It's a very interesting story, so I recommend you to look at that. Anyway, the main thing is that this idea of using frames is 150 years old. Now, in fact, it's so embedded that around 2010, Eric Fossum, here's a picture of him, who's one of the three fathers of modern CMOS image sensors, defined at the image sensor workshop. You know, there's an international image sensor workshop that brings together top 100, you know, camera chip designers in the whole world. He said, I know what the perfect image sensor is. Do you know what it is? Yeah. It has infinitely small pixels, and each with infinite dynamic range, and it can do infinite frame rate. That sounds really good, right? Except for one thing, and I'm very ashamed to say that I didn't stand up and say this at that time. What's the drawback of this? Yeah, infinite data rate, infinite redundancy, and infinite power consumption. But that's exactly how these guys were thinking in the image sensor community. They weren't thinking that they had to reduce the data, they just had to supply everything possible. Now I'm going to show you some beautiful history.
So there were cameras that were very high speed, right?
Yeah, super high speed, but they burn tons of power and very expensive.
Yeah.
Yeah, you need tons of light, you know, like arc lamp power. Yeah, you can, there's a wide market of cameras, like all kinds of specialized cameras. In fact, you can buy cameras now that do frame rates of billions of frames or even hundreds of billions of frames a second. Hundreds of billions of frames a second, and they do that by actually storing the samples around the pixel. While the camera's exposing, they actually store samples right around the pixel, and then they read them out later. It's really amazing technology. Yeah. Okay, so there was a fellow named Fukushima who anticipated all of neuromorphic engineering by about a decade or even 2 decades, because in 1970, working at NHT research labs in Japan, it's actually an industrial research lab, he designed a series of things called the Reticon and the neocognitron, and realized this is from the period 1970. I'm sure many people in this room were long before you were born, up to 1987. In fact, one of the things he did was called the Reticon, and in this beautiful paper, an electronic model of the retina, published in the Proceedings of IEEE in 1970, this paper is literally 1.5 pages long. 1.5 pages. It's a very beautiful paper. This is his silicon retina. It's actually a wall of electronics. It was capable of taking a spot input like this and turning it into an edge-enhanced output, like the real retina. It had like the resistive networks and so on that you've probably learned about in the course already. And this kind of inspired him to think, you know, maybe we can build an electronic brain. And so he went on, have you talked about Fukushima, by the way, in the course?
No.
Yeah, so I found this, I want to play this lovely video. I think it's just a lovely video. Hi, nice to see you, Andrea.
So he won the Franklin Medal a couple of years ago for the neocognitron.
Yeah, okay, so now I'm going to show you the neocognitron. This is a video that was produced by NHK following this work.
Recently, neurophysiologists have discovered many new facts about the mechanism of the brain. In the visual cortex of the cerebrum, for instance, neurons are found to respond selectively to local features of a visual pattern, such as lines and edges in particular orientation. In the area higher than the visual cortex, it has been found that cells exist which respond selectively to certain figures like circles, triangles, or squares, or even to a human face. Accordingly, the visual system seems to have a hierarchical structure. Such a neural network is not complete at birth. It gradually grows, adapting flexibly to circumstances after birth. Then let's see how the neocognitron recognizes patterns when it has finished learning.
I had to cut out some
If
stuff.
a pattern A is presented to the input layer, only the one cell which corresponds to pattern A is activated in the deepest layer. The input pattern is first observed over a narrow range by cells in the lowest stage, and several local features are extracted. At the next stage, these features are combined by observation over a wider area, and higher order features are extracted. This operation is applied repeatedly through the pattern. Positional errors of the stimulus features can be tolerated a little at a time at every stage of feature extraction and integration. Let's take the feature extracting cells in the network are called S cells. After each layer of S cells, a layer of another kind of cells called C cells is inserted. Each C cell gets signals from a group of S cells which extracts the same feature, but from slightly different positions. The C cell is activated if at least one of these S cells is active.
You recognize these are simple cells and complex cells, right?
In the whole network, layers of such S cells and C cells are arranged alternately. The operation to tolerate the positional errors a little at a time in each stage, rather than in one step, plays an important role in endowing the network with an ability. This system is operating on a mini computer, and it can even operate on a microcomputer.
This is really funny here. You can give it state of the
Let's
art.
draw a numeral 2 on the tablet.
From the analysis of the stimulus features, the input pattern is recognized as 2.
This goes kind of slow, right?
Now the response of the cells of the network to various patterns will be shown. You will see
the rest of this. I encourage you to go look at it.
recently
Anticipated so much what is now considered convolutional neural networks, like 2 decades before Jan LeCun, came and figured out how to really make them work correctly.
The learning helped.
Yeah, the learning, right. He had a simple-minded learning scheme, and there was no backprop or anything. It was handcrafted, basically handcrafted. But the idea of max pooling, which I'm sure everybody in the room knows, comes directly from the idea of complex cells, pooling simple cell output in cortex. Okay, so I'm sure Carver was aware of this kind of work. And at this time, Carver, I forgot to bring the book along. Carver Mead at Caltech, was very famous already. Invented basic kind of transistor, and he had written together with Lynn Conway the textbook for digital circuit design, which was used industrially for more than 20 years. Right? It was the beautiful, most useful digital design book. And during the whole time, Carver was a physicist at heart. And he had explored the biophysics of voltage-sensitive nerve channel memories as kind of a holiday from working on the digital chip design, which had by then already become very industrial. He became interested, how do these nerve channel proteins actually work? How are they voltage sensitive? Are they exponential with voltage, just like transistors? And that got him generally interested in the idea, could you use electronics to try to understand how the brain works? It wasn't really a method of building a new technology, but more like understanding how the brain works. And so we teamed up with this young Ph.D. biology student who knew nothing about electronics, Misha Mahaold, but very smart, in the physics of computation lab at Caltech, and they set out to try to build silicon retinas. Now, realize at this very same time, Eric Fossum at JPL was building the very first CMOS image sensors. And Carver considered this rather mundane. In fact, he showed one of the early chips that he did to Eric Fossum, and he said, oh, look, this is the zero order retina. And then he went off with Misha and started building actual integrated silicon retina chips with Misha. And in fact, this resulted in the most famous image probably from neuromorphic engineering, which is this cover of Scientific American in 1991. This is silicon sees a cat. This retina on a chip mimics the functions of cells in the human eye. And this is actually a picture of Misha's cat. And it took her like 3 days to get this picture because she had to get her cat to pose in front of the chip. And then she had to shoot with a normal camera the output of a multi-sync monitor, which was showing the live output. Because there's no way to capture the output on a computer. It was actually just a live output, or you could look at individual pixels on an oscilloscope. But there's no computer interface. It was just like plug the chip in and it would make a direct video output to a multi-sync monitor. And I came across recently a treasure trove of files that I had saved from that time. These are all the hundreds of original chip designs from Carver's lab in Caltech CIF format. And you can still load them directly into K-layout and actually look at the individual transistor level. Realize this is chips that were designed 30 years ago. It's remarkable. And you can still use CIF format to look at them. And this is the chip that actually made it onto the cover of Scientific American. It's called PRET40. It was designed around 1991. It's a scanned hexagonal layout, retina with horizontal resistor, pseudo resistor surround that computes the spatial temporal low pass filter. So this is the actual chip design. It had like 64 by 64 pixels. The pixels were huge, about 160 microns on a side. Consider now that state-of-the-art cell phone camera pixels are less than 1 micron. This is like thousands of times bigger. Of course, that was 30 years ago, right? And everything's been scaling by Moore's law. You guys have already learned in the class how this HRES works, right? You've talked about this pseudo resistor. Yeah, so I'm going to show you because I think the circuit is really quite interesting. Here you have a logarithmic photoreceptor that models the biological photoreceptor. And then the output of each pixel of this thing is actually a bidirectional current computed by this transconductance amplifier. And it's taking the difference between this photoreceptor and some other voltage. This voltage here, which is actually the average of the neighbors in the nearby surround, which is computed by this pseudo-resistive network. There's a transverse conductance. This one is just a transconductance amplifier. And there's also lateral pseudo-resistors, pseudo-conductances. And you see how the circuit works? It's actually an extremely clever circuit that Carver came up with. This looks like a normal 5-transistor transconductance amplifier, but there's an extra diode-connected transistor inserted here, right? So what that does is, this thing normally just has a 0 voltage difference here. This diode-connected transistor biases the gates of all these FETs above their source drain by this bias current amount. So that sets the conductance of these transistors to the neighbors. So by playing off between this transverse conductance and this lateral conductance, you can set the space constant of the spreading of this network. That's the principle. It's really beautiful. On the right, you actually see the layout of these pixels. You can see here one pixel. This is a hexagonal layout. You see, there's one pixel. There's a photodiode right here. And all this light area are all these pseudo resistors. You see, it's like half the total pixel area is just for the spreading network. In fact, you can trace the individual connections. Like, for example, this one right here is this one of these transistors. And you can see the wire going off here to this pixel. And this one here is the wire going off to this pixel. So it's a lot of wiring. It's expensive. Is it worth it to do all this smoothing electronically? That's the question. And does it really help? Because what they wanted to capture was a spatial processing done by the Retina, which is essentially like a high-pass spatial filter, right? And if you look at what actually did this on Misha's chip, you see, I've got this dumb yellow thing here. There's again the same idea. I have to hide this dumb yellow thing here. Sorry, let me just go out of this. So I'll just move this out of the way and show it again. Okay, so here is Misha's Retina, again, with this hexagonal surround. This is, again, Misha off her multi-stick monitor. You can see some of the drawbacks, very low resolution, right? Gigantic pixels, tiny fill factor, like 95% of the photons just get thrown away without even having a chance to get converted to electrons. And a biggest problem probably was the matching. You see here, the white wall, which is up here behind Misha, is supposed to be white or gray, but it actually looks black and white here. That's directly due to transistor mismatch. And so if all the problems of trying to bring neuromorphic mixed signal circuit technology to mass production, I would probably call that number one. It's a problem of precision and the fact that all transistors are not built the same. And so now I show the people that are not aware of this area. Let me hide this thing again. What is this problem fundamentally of transistor mismatch, which Carver actually first characterized? So let's look at the ideal transfer curve of one transistor and what inspired Carver to think that it's like a neuron, right? So this is a plot of the drain current on a log scale versus the gate voltage. You see the drain current is actually exponential with the gate voltage. That's like the biophysics of nerve channels that are voltage sensitive. They're also exponentially open with some probability that's exponential with the voltage. And that's how it should look. And all this region up here is where logic circuits work. This is the beautiful 6 or 7 decades of current brains that Carver really loved. And it's ironic that Carver himself wrote the famous paper in 1972 predicting transistor scaling that predicted you would go down to 5 nanometer transistor size in 1972. And he had this image in the paper, or at least one like it, that showed the fabrication of one transistor's source and drain. So the current in this transistor flows from the source to the drain through the channel region. And these blue and red dots here are where the dopants are implanted to set the energy or the doping level of the N and P regions. And you see the channel region here? These are the discrete dopant ions, and they fall on the transistor when you're fabricating it, just like rain falls on the street. Sometimes you're going to get more ions there, sometimes less. If you get more ions there, the energy barrier is higher. If there's less, it's lower. And so if you actually take 300 transistors and plot their drain current versus gate voltage, you get a distribution like this, where the threshold voltage, which is where this thing starts to bend over, has a Gaussian distribution, right? And when you go through the exponential, it actually turns into a log normal distribution of current with a very big spread. And especially because you're doing an exponential of this Gaussian, you get a big spread of currents. And so that's why you have difficult to make precise computation. I think that's the fundamental reason. And so when we were given the job as part of our European project, I actually inherited the project from Jörg Kramer, to build a pixel that actually would work. Patrick and I, who actually came from physics, said, this is Patrick Lichtsteiner here. We said, look, let's just go back and simplify everything. We won't try to do space. We'll just do time. We won't try to do anything fancy. We'll just try to make something precise that somehow gets at the idea that the retina produces a sparse output, which is spiking, and that it has high dynamic range, because those are the things that might actually be valuable. And so we came up with this rather simple circuit design, which I'm going to talk about in the end. Let me see if I can actually put my laser here, where you take the photodiode photocurrent and change it into a voltage logarithmically. This is all continuous. That's kind of a model of the cone or rod photoreceptor. Then you just completely block the DC with a capacitor, because in the previous thing, you saw all the slopes were the same. It's the DC offset that varies from pixel to pixel. So we just block that. We don't care about it anyway, right? If you care about changes, you don't care about the DC. And then we amplify that change, which is stored across this capacitor with a nice precise amplifier. And then we compare it to an on and off threshold with a comparator, but it's not clocked, it's just continuous time. So anytime the change, since you reset it, exceeds this threshold, on or off, you can generate an on or off brightness change event. And so as a result, the pixel output is very simple. It's just a stream of brightness change events, where brightness change means log intensity change. Very simplified view of what real retina does with the dozens of clusters of real ganglion cells. And that turned out actually to be useful for real problems, that are not served by traditional image sensors. And it was inspirational, but there were problems. What's the problem? Now you don't have a DC pathway, right? And a DC pathway is useful, and the pixels are big, and the fill factor is small still. So how can you actually deal with those problems? So, but the concept here is beautifully illustrated in this video from Davide Scaramuzzo, who is a roboticist, computer vision person who took up this technology, generated this video comparing a standard frame camera with the DVS camera, dynamic vision sensor, in response to this rotating dot. You see, normal camera just puts out the frame over and over again. DVS just stops putting out data as soon as you stop moving. Of course, now you don't see anything, right? Normal camera, if you run it really fast, the dot gets blurred out and it gets aliased. This DVS ideally should just make a nice tight helix of events. So that's the concept that the computer vision think about when they think about this sensor. They don't care how the pixel works at all. They don't even understand it. For many years, in fact, the computer vision people were saying that this sensor has no motion blur. It's not true. It has motion blur, but they thought that it had no motion blur. And they thought that the pixels actually have a latency of microseconds in response to brightness change. It's not true. That's just the best latency that we could get, that we put in the title of our solid state circuits paper. All they read was the title because they couldn't understand the rest of the paper. So they always claimed for years that these DVS cameras have microsecond latencies. And I kept having to tell Davide, look, that's just not true. They actually have real latency. It's sub-millisecond, but it's not microsecond. So finally, they're kind of catching on to that now, that these things have physical limits. But I tell you quite honestly, most computer vision people don't even know what an RC low-pass filter is. So anyway, so what is a DVS missing? It's missing this DC pathway, which all biological vision systems have. This lovely simplified illustration from Bob Roddick's book on the retina. You see, it actually starts at the retina with different classes of ganglion cells, and in the thalamus, the lateral geniculate nucleus, with 2 layers devoted to magno, 4 layers devoted to parvo, and even in the middle, the layer 4 of area V1, 4C alpha and 4C beta. These layers of thalamus actually project to discrete layers of the input layers of area V1. And these different classes of cells, which are genetically different, actually consist of a sustained pathway, which is color selective. That's how you're seeing this image right now. It has high spatial resolution, but it's rather slow. The other pathway, which is the magno pathway, which serves you anytime you're walking around the environment or moving around and you're not bumping into stuff. That's the magno pathway, the thing that attracts your attention when motion is in the periphery. And that's actually monochromatic, it doesn't see color. It has low spatial resolution and it's fast. And this partitioning, which I'm showing now for primate vision, is true across all mammals and birds and even insects. They all have this they split the job up into either a bunch of very slow, high resolution cells or much fewer, but much faster cells. They don't try to cover both, right? Because it's too energetically expensive. And so how can we do that with this event camera stuff?
Oh, by the way.
Yes.
Just a question. So you mentioned that the sustained pathway has a higher spatial resolution. How does that happen? So is
The
it?
receptive fields are smaller.
Oh,
that's
so
all.
it's denser, kind of like.
Yeah, denser. More densely tiled. Yeah, by the way, thank you for asking these kind of questions. It just means they're more densely tiled. Yeah, the story is more complicated than this because the fovea is largely sustained and the periphery is almost entirely transient. You have the illusion of seeing color because the very low density of cone photoreceptors in the periphery. It's almost all rods. I mean, it's almost all transient ganglion cells in the periphery. It's a complicated story, but the general principle is that the biology splits up the job because it can't do both economically. And in fact, your eye, guess how much power it burns? Each retina of the human eye. What do you guess? The number? A watch?
Milliwatt micro.
Oh, very good, because you guys know this stuff, right? It's about 3 milliwatts, people have estimated. The whole brain's about 10 watts, right? Each eye is about 3 milliwatts. Turn this thing on, it's about 300 milliwatts, right? The camera here, it's still hundreds of milliwatts. So your eye's doing a lot, for a little bit of power. Anyway, so how can we now add this back into the idea that you have a sustained pathway? Well, it's real simple. Add the frames back in. They're analogous, and everybody understands how to use them. Let's just add frames back into the DVS. And so we did that. We took this DVS pixel, which I showed you before. I'll explain the principle much more clearly later. And said, look, you know what? We have a logarithmic photoreceptor right here. But the current is just flowing through this thing. We don't have to throw it away into VDD. We can just integrate it over time and make pictures out of it. And it doesn't cost anything to do that. It only increases the pixel area by 5% or so. So we add a frame-based readout. Now this is simplified, right? You have to use double sampling and stuff like that. You have to put A to D converters on the edge of the chip and so on. But anyway, the principle is very simple. You only add 2 or 3 transistors to each pixel. You can add a frame readout and you preserve all of this. And that resulted, and you actually share the same photodiode. So you have like a magno and a parvo pathway within the same pixel, sharing the same photons. It's pretty cool. So economical. And so that's why we came up with the Davis in 2014. This is Christian Brandley, who went on to found Insightness, which got bought by Sony. That team is largely part of Sony now, Christian and Rafa. And this is the video of Christian catching football. That's, you see, Neuroinformatics. That's the sign at the Institute. He's catching a football. You can see the frames, and together with the frames and ahead of the frames are the brightness change events. So these are just the brightness change events. You see it was quite noisy at that time. Every time you read a frame, you'd get some events. Or you could just show the frames. You see the aliasing and the motion blur? Yeah, so now you have both pathways in one chip. You don't have to use the frames, you can if you want, but they're happening concurrently. Now, what's missing from that? Are we still missing something? Thank you very much. That's why in the same project, the same wonderful European project, another PhD student, Chenghan Li, who was the lead chip designer at Innovation, did the C Davis. Now this chip is practically unknown because we never sent it off to ISSCC or CICC, and we just published it in the International Image Sensor Workshop. It's a red, green, blue, white, color, VGA rolling and global shutter dynamic Davis, basically. And I'll show you the layout first. So here you have actually each pixel or macro pixel here actually has 4 pixels within it. One Davis pixel, which is all the pink area, it has a white buried photodiode, and then surrounding it are a red pin photodiode, green pin photodiode, and blue pin photodiode, 4 transistor global shutter, active pixel sensor, image sensor with pixels designed by Tower Jets. So this mixes together in a heterogeneous way a standard image sensor with color, just like you have in your phone or industrial camera, because it's global shutter, means that the pictures are taken synchronously, and with this event stream. And here's a rare video, one of the few rare videos of this C Davis working. See, it's getting this color picture of the Macbeth color checker chart, and it's also making events at the same time. These are the brightness change events. Where it's gray, there are no events, and where it's black or white are the on and off events coming from the pixels asynchronously. And here are the color frames. And unfortunately, we never actually made a camera for this that people could buy and use, through innovation, because the quantum efficiency is rather low. It needed quite a lot of light to see for some reason that we never quite determined. But it's unfortunate because it really was quite cool chip. You really had standard RGB frames, and then you had these nice sparse events that you could work with in between. What's missing with this? These are still big pixels, right? So what do you do about that? Okay, so then at that point, this started leading to an evolution, industrial evolution, of these sensors. Let me see if I can get out of this, where industry started developing these sensors as well. And this is a plot of the pixel pitch in microns as a function of year. Now, remember back in about 1990, which is way back over there, the pixel's like 160 microns, right? Misha and Carver are the ones I did at Caltech. And then our first DBS was actually only 16K pixels, right? 128 square. But then they just basically followed Moore's law. You know, Moore's law was kept going here at this whole time. This is the pixel size, and this is the number of pixels on the whole chip. And most recently, industry standard is like a megapixel DBS. And the most recent pixels are down around 3 microns. Compared with 1 micron, they're still 10 times bigger than a smartphone, but they're not much different than you have in an industrial camera, where it's typical to have 2 to 4 micron global shutter pixels. And so it really is scaling. Now I want to show you one recent publication, which I think from last year's, how is this scaling been possible? Well, you may not know this, but actually your phones in all your cameras are increasingly becoming like retinas. They're becoming 3-dimensional, or at least they're becoming stacks of wafers. Instead of being just a monolithic wafer with photodiodes directly integrated to them, nowadays, Sony and Samsung and OmniVision, all the other bigs, are producing camera chips that are stacks of 2 wafers that are bonded together. And the top wafer does the phototransduction, that's like the rods and cones. And then at the pixel level, each pixel is copper bumped to a bottom wafer, and the wafers are pressed together, so the bumps actually make connections, and the bottom wafer has all the circuits. And so in this scheme, in this paper from ISSCC from 2020, from Sony and Prophecy, they use this technology here. They got down to 5 micron pixel with 80% fill factor, almost completely active. And you see what's going on here. On this top wafer here, you only have 2 NMETs and a photodiode. That's all. The bottom wafer here, with the bias current for this photoreceptor, everything else is on this bottom wafer, and that's about 50 transistors, very densely patterned on the bottom wafer. Okay, so that it was actually Samsung that did it first, but their chip didn't work very well. And the Sony Prophecy guys were able to get a chip that's stacked like this that actually works so well that people can buy it and play with it. Now, it's really taken off. Last year, actually this year at ISSC, 3 out of the 8 papers in the image sensor track were about something like an event camera. And I'll show you one work that I consider particularly impressive. And this is from OmniVision this year. And this picture looks very complicated, but it's really cool what they've done here. So you see, actually, they have a macro pixel, which consists of 4x4 pixels, and one of those is a DBS pixel. And it's fabricated on 3 wafers that are stacked together. 3 wafers. Now it's really becoming 3-dimensional. The interesting thing is that in this 3 wafers, this one pixel, which is like a DBS event generating pixel, is copper bumped to the circuits on the middle wafer. And in this middle wafer, you have the DBS pixel change circuits, the handshake circuits, the time to digital converter, and things like that. And then the other pixels that are part of this macro pixel actually come out, and they're connected by metal lines across the chip. And at the edge of the chip, there are through silicon vias that connect from the top wafer to the bottom wafer. This is much harder to build. You can't build this at the pixel level, but on the edge of the wafers, you can build these through silicon vias and actually connect from the top wafer to the bottom wafer. And then on the bottom wafer, they have the column parallel A to D converters, the scanners, the event signal processor that does noise reduction and so on. And they also have a standard image signal processor and a mobile industry processor interface, so they can send the data out to a smartphone. This is pretty cool, right? But this is expensive stuff. There's no way an academic group can do this kind of stuff. This is probably a $10 million turn. This is all state-of-the-art stuff, right? There's no way academic groups can actually compete in this area. So we're not going to compete in it. If it's going to take off, it's because industry decides this is worth it. And finally, some customer will buy in and it'll go into mass production in some form. Yes?
What's the difference with in the fabrication of the motherboards? Because the motherboards use many layers, no?
Yeah, this is at the silicon chip level. Actually, each of these is a CMOS chip, not a passive interposer. These are CMOS chips which are thinned. thinned down. This is back illuminated actually, right? So it actually thinned down so and it has micro lenses, color filters, and so on. This is now standard for image sensors that they shine light on what you would call the original back of the wafer, which has been thinned down, and so that all the metal and stuff is actually hidden. So the light is directly hitting the back of the wafer. And then this is copper bump. This is all standard now for image sensor, most mass production image sensor technology. It's very sophisticated. It's not standard CMOS, right? It's gotten quite fancy. In fact, even between pixels, they have special etchings to isolate the pixels. They etch in special micro lens structures. It's really quite cool what's going on in image sensor technology. But they say, look, we're making images again. That's burning too much power at the system level. We're just burning too much power. We can't leave the camera on, because if you think about it, if you leave one of these 10 megapixel cameras on all the time and you're running it at 100 hertz, you have to process 1 billion pixels a second. 1 billion pixels a second, and most of them are totally meaningless. So they say, maybe that's interesting. We want to be able to leave the camera on, and do stuff all the time. That's why they're interested. They haven't found a customer yet, but they clearly want to do more than just sample the intensities.
Oh.
And so that's why there's been a lot of industrial development lately.
Just
Yes.
another question about, I'm thinking whether there is a contradiction between the DVS, advantages and this kind of shrinking the pixel size. Because the DVS features like the high speed and high efficiency, right? But I tried to use the higher spatial resolution DVS, but obviously it will cost much more, the processing time and the cost. It really deserve it, or the DVS really need to be, fighting?
Question of application. If you want to run a high resolution camera all the time, for example, AR, VR application, and it's burning 1 watt per camera to do all the acquisition and processing, battery won't last very long. Suppose you could do it with these events, the same job of visual odometry and pose estimation and object recognition, and you're only burning when you're moving your head around.
Oh, no, I'm not comparing the DVS with RGB. I'm comparing DVS with DSL. For example, if we're only focusing on this kind of the dynamic starting or the dynamic frame rate thing, so why not use the lower resolution DVS instead of using very high resolution? Spatial resolution.
It depends on the application. Lower resolution, which I'm going to show you. Thank you for asking that. That's a very good question. I'm going to show you a lower resolution thing that we've done recently that might actually have application in neuroscience. This is like for smartphone technology where you need lots and lots of pixels so people can take pictures. Okay. Because most people are buying phones now to take pictures, right? Not to make calls. Well, they want to do social and they want to take pictures. So it's the market, and all the big companies are betting on spectacles in a decade from now, that everybody will be wearing spectacles instead of carrying phones, right? But we're still a decade away in terms of the power and everything to achieve that. That's the kind of place where a sensor like this would maybe really make sense, where battery is premium, right? You can't carry around several watt hours like you are now. Yeah. Okay. So
I have
yes.
one question. I find this tremendously interesting. But when you look at the retina, the pixel in the retina is circular, while we have it here just square pixels and in silicon.
Yeah.
And so what differences can you expect that actually will be inherently different from the real biological?
Yeah, so the question is a valid one. How much does it matter that we're completely ignoring the vast complexity of real retinas with 20 different classes of ganglion cells, varying receptive field size, rods and cones that cover different ranges to cover 9 orders of magnitude? It's simply a matter of economics. We have to simplify it now because we can't build biology. It's just too expensive. We have to keep the fill factor up and we have to keep the pixel size small. Otherwise, people won't pay for it, right? Because ultimately, they're going to pay for pixels. And ultimately, every company gets in what's called the megapixel race. You want more pixels that are equal quality for less money, right? Because everything is by silicon area. It's $4 a square centimeter. That hasn't really changed. The bigger your chip, the more it costs, the less profit.
Yeah. Now, you said that pixel is a micron size, and you said that is very astounding how small it has become.
Yeah.
But 1 micron size pixel in terms of data storage in a hard disk drive is nothing. In a disk drive, you store a million times
more
on a pixel than
but it's close to the optical resolution of light, right?
That is my point.
Yeah, they're approaching
Makes no
optical
sense,
resolution.
right, to make it much smaller because
Doesn't
of
make
the
sense.
wavelength of light
Yeah.
being 400 nanometers or
That's
so.
what they said about that too,
If
though,
you
right?
make it smaller, it doesn't bring you any effect anymore.
Yeah, so that's why they look for other stuff to do, right? They find these, they went as far as it's possible to go and still, sense the variation of light, given the resolution of the wavelength of light. What are they gonna do now, right? Okay, we have to actually do something different, right, than just sample the intensities.
Yeah.
Yeah, so, they're creative people, right? They want to do something interesting. They don't want to just build the next generation 100 megapixel, 200 megapixel. That's boring for them. They want to do cool stuff, right? So this also motivates the work and the dream that maybe they do more than just take pictures. And finally, this idea is penetrating to the big semiconductor imaging companies. It's a long time coming, right? Because they had to first sell cameras, right? It's understandable. Okay, so now I want to show you something that we just got working. It's quite a cool device. It's called SciDBS. We're just sending a paper off to CICC about it. It's the project of Rui. It's a clever, very clever, creative Portuguese PhD student that's about to finish. And what he did was, to the standard DBS pixel that I just showed you, he added an adaptive preamplifier, auto-centering preamplifier before the change detector that detects the events. And it has better bandwidth control to limit shot noise. And here's how he tested it. This is quite cool stimulus. You notice that he rotates this disc and it consists of these different sectors here. And you might notice that there are high contrast edges, which are 20% contrast change. And there are also low contrast edges. In fact, can you see this contrast step right here? You can see it, right?
Yeah.
Just barely. Can you see the 1% step here?
Yeah.
You can see it. I can't see it at all. Yeah, I can just barely see it here, about this 2 point. Yeah, in other words, these small contrast steps are barely perceptible. You can see them because they're distributed. But imagine one pixel looking at that very small change of brightness. It's a tough job because it's buried in a lot of shot noise. And so here is actual data that is collected under 2 realistic illumination conditions, where we light up this chart with 12 lux, that's like a bedroom at night, or 0.2 lux. This is actually 0.2 lux light shining on the chart. That's like a very bright full moon. This is dim lighting. That makes it especially tough. Now realize, to do this, you have to make it very slow. You have to really filter the hell out of it. So the pixels are quite slow. But this is how the Davis 346, which I'm going to demo for you, does. It only sees the 20% edges, right? It sees them, but they're buried in tons and tons of noise. And we set the threshold to limit the noise to a particular level. And this is the Prophecy Gen 4. It says even worse than the Davis, of course, because it's somebody else's chip, right? Okay, but actually it really does do worse, right? It's not as sensitive. If you try to make it more sensitive, you just get extreme amounts of noise. And here is this SciDBS. This is with pixel binning mode. So it has a pixel binning mode. It still has the same number of pixels, but they get averaged together. But actually you don't have to use that. So this is under the 12 lux scene. You see actually the plus and minus 1.7%, and you can even see the minus 1% off edges. And you can clearly see these 2% and 4% changes very clearly. It's really much better than the state of the art. And here's the actual video of the data.
So how long were you collecting photons there?
No, they're not. The events are integrated here for about 100. This is very slowly turning disc. This is integrated for about 150 milliseconds. So this is showing 150 milliseconds of on and off events, right? It's like an exposure accumulated like a 2D histogram for 150 milliseconds. And here is the actual sensitivity curve measured over the array of pixels by Rui, very carefully measured. Never had a student who could measure stuff so carefully and so beautifully. So this is the fraction of pixels responding to a step of a particular contrast in E-fold. And you notice these dash curves here are standard DBS that I've showed you before. The minimum contrast that you can set is about 15%, right? You need about a 15% at a particular noise event rate. But by activating this new preamplifier and the bandwidth control, you can get down to 1%. It pushes it down by another order of magnitude in sensitivity. And this is very exciting for people that want to do long-term recording at high time resolution and still want sparse output, like the people doing neural voltage and calcium imaging and the people doing particle flow velocimetry and things like that. These pixels are large. So this is not a thing that an industrial company would do, because it's not a mass production thing, but it's a kind of scientific sensitive. So this is pretty exciting for us. It's the first time we actually achieved this high sensitivity.
So,
Yeah, and here's the actual video of that working. This is at the 12 lux scene. Yeah,
what is the reason that the preamplifier improved that one?
yeah, it improves the input. I'm going to talk about this on the blackboard. The thing is, it amplifies this photoreceptor output before it gets to these comparators that have lots of mismatch. The comparators have mismatch, right? And if you set the threshold too low, some comparators just fire even if the pixel shouldn't, just because the threshold is such that it's on the other side of where it should be. So it's the mismatch in the comparators and the change detector. If you amplify before that, the input referred mismatch gets reduced. I'll talk about this exactly afterward. Yeah. So more gain before you get to the change detection is the key principle to get the precision here. Right? The higher the gain, the more precise it is. But of course, the higher the gain, the more data you get because the threshold is lower. You know, so the more sensitive it is, the more events. You may not want that. You may not care about it. You may want to limit the data rate. So you may want to actually operate the circuit sometimes in this low sensitive mode or in this very high sensitive mode where it senses tiny changes, because this makes tons and tons of data and lots of noise too. It's so sensitive. Is this clear?
Yeah, but what is the windows of the windows of the sensor of the light and the band?
The windows?
What is the wavelengths that they receive?
Oh, this is white LED light. It's like a standard white LED light. Yeah, visible light.
Oh.
This is just silicon. It's not in near infrared anything. The question is what wavelength? It's monochromatic, but we use white LED. But it's broadly sensitive over the visible. All these silicon chips, you know, with bare photodiodes, there's no color filters here. They're just broadly sensitive. Very fortuitously for human society, that silicon happens to be very sensitive to visible light. In fact, it's perfect for seeing visible light practically.
But
No reason that it should have been that way, but if that wasn't true, it would be much harder to build camera chips, right? You need some exotic conversion material. Yeah. Yeah, maybe that was God smiling on you know, artificial vision, right? Silicon, you know, the most abundant element in Earth happens to be good for building eyes.
Yeah, because
electronic eyes.
They change the sensitivity with the wavelength, right?
Yeah, of course, there's some quantum efficiency curves.
You have some.
We don't have the curves for this chip yet, but they're the same as any. They're just standard buried photodiode. I'll explain what a buried photodiode is later too. I hope, if you ask me. Okay. Okay. Yeah. So that's it. That's kind of a nice summary, I hope, of the very early history all the way up to the present of the silicon retina business. Did anybody have any question? I'll just do a demo then. Yeah.
So the preamplifier is along with calibration.
We're not disclosing what it is. This is top secret right now, man. You're just lucky that you see that it works, man. This is supposed to show you that it works, right? No, there's a very nice circuit that Rui came up with for this auto centering preamplifier. Yeah, that's the secret recipe. Anyway, the thing is that very important that you need to be able to control the bandwidth very slow so you can filter the shot noise, because we finally understand, literally took 15 years to understand how noise works in these pixels. And we finally start to understand how noise works and how to get rid of the noise. In fact, is Ryan here right now? Is Ryan Kastner here? Yeah. He couldn't make it. Yeah. Yeah. Hi. Nice to see you again. Yeah, we did a really nice project on how to get rid of this noise, you know, because it's not correlated. It turns out the noise is actually totally uncorrelated. So it's quite easy in principle to get rid of it. The real signal, of course, is very correlated, but the noise is totally uncorrelated. And so you can quite easily filter it out.
Are you doing like ESP template matching stuff?
No, that's a totally separate subject. I can demo it. I'll show you how it works at least.
How does the noise vary with the pixel size?
The bigger the pixel, the less the noise, because you're collecting more
Okay,
photons.
so you have big pixels, right?
Yes.
That's why you have
In
big
principle, we can get down with this pixel design. If we burn lots of power, we can get down to 2 times in principle, the photoreceptor output can have output voltage that's about 2 times the shot noise of the photons with very high quantum efficiency. And we burn lots of current in the amplifier. We can get down to about 2x the shot noise of the photons themselves. You know, in practice, more like 4 times. So it's a long ways from what you do in the smartphone cameras. that literally almost get down to sub-electron read noise now. You know, a few electrons read noise in mass production. It's really incredible.
Can you make a prediction of how our cell phones will look like in 10 years?
No, I'm not a pundit. We'll do that later, right, in the discussion. Yeah, I'd rather do a demo.
Okay.
Yeah, no, you won't have them on, you'll have them on your phones, but mostly they'll be here in your spectacles. Right? That's my prediction. And that, at least that's not my prediction. That's all the big, you know, mobile electronics companies are predicting, that the next big thing is going to be some kind of spectacles.
With or without AR?
Yeah, with or without, but it'll be the accessory that everybody has. And you'll interact with it with gestures. It'll help you hear better and see better and record your life and help you see what you're looking at and all that kind of stuff. That's the big thing.
What do you think?
I hate Minsky, you know. I really hate Minsky, so I don't want to make any prediction like that. Yeah, Minsky is the one who always makes these problems. He stopped doing any real engineering, right? He just makes predictions now. Yes, I don't like that stuff. Sorry. You like it, right? You like these predictions. I don't think it has much value. Maybe for business people it does. Okay. Okay, so this is actually the output of this Davis camera. It has 346 by 260 pixels. It's not very high resolution, a quarter VGA. VGA resolution, you guys remember VGA? It's 640 by 480. And what you're seeing is actually looks like images, but actually, thank you, Gert. We'll look at Gert there. If I move it around a bit, you can see a nice kind of picture. It's a grayscale picture, but actually those are individual events. In fact, yeah, this person nicely waving now. Let me see if yeah, now you wave your arm again. Oh no, I don't have sound anymore. Oh yeah, do you hear it? Let me turn off the sound.
Yeah, we can hear.
What's this sound?
Yeah, wave your arm and it's probe the receptive field. No, the blue one right here. The rest of you guys can wave and all that. This pixel right here. You hear it? Oh, put your hand across it. You're crossing your wrist here. Yeah, you're listening to that pixel spiking. Right? That's the only output of those spikes coming from the pixels. Actually, where it's gray here, there are no vents. And where it's white, it means that it got brighter. And dark means it got darker. I'll show my edge here. Maybe this is a bit easier. You see, my hand is brighter than this floor, right? So if I move it down, I get on events. Leading edge of my hand, so on events, and off events, trailing edge. Makes sense, right? Where my hand leaves, the picture gets darker. So I get the stream of these brightness change events. And you can hear the individual pixels. Maybe it's best to show you that they're actually discrete events. So if I look at these events in space-time, there's a lot of noise. There's some hot pixels there. But now this axis is space, and coming out towards you at an angle is time. The last 60 milliseconds. I can increase that, perhaps slow it down a bit. It's 100. Okay, so now it's like 500 milliseconds of events. Now what I'm going to do is slightly cheating. I'm going to turn on a noise filter. So get rid of this uncorrelated data. Now if I wave my hand like this, hopefully it didn't crash it. Okay, let's see if I can just freeze that. Okay, so now it's actually live. I have to freeze that. Yeah, it's paused. Okay. Okay, let me do the real experiment. Let me go live again here. Get rid of that. And that's a rolling thing. Let's go back to the live view. Let's make it go again. Let's make it, let's speed it up again. Okay, so now we're live again. Okay, so that's more like a picture. Now, this is actually a database. So now I'm going to do something quite cool, which is to turn on the frames at the same time. So these are the image sensor frames running concurrently with the events. Now I'll change the events so that they're shown in red and green. Now you see somebody can wave their arm. You see now, and I'm going to slow down the frame rate a bit. You see the events coming out ahead of the picture? Yeah, if I just move it, if somebody moves their arm there, perhaps you can see that a bit better. Right? So that's the only about it. If I turn off the frames, you get only the events, very sparse. These are discrete signed binary events indicating these brightness changes, or I can turn on the frames. Now, this picture,
How many? Five.
What?
yeah, I'm running this at a very low frame rate now, 5 Hertz, you know, just to demonstrate that it's sampled that way. I could run it faster, okay? Okay, but now I want to show you something quite cool, which is what happens if I now reduce the brightness of the scene, okay? So let's stop down the lens here by closing the aperture. I'm gonna make it really dark. Yeah, I keep closing it down. Now you see this exposure time here? There's an auto exposure loop that increases the exposure time for the frames, right? So that it kind of keeps the pixel gray level the same. I make it darker. It keeps getting a picture. The picture is not bad, even with an exposure time of like 370 milliseconds. It's not a great picture, but now let me move the camera. I'll turn off the events for a second. The instant I move the camera, this is what happens. Because of this long exposure time, it's totally motion blurred. You can't see anything at all, right? Because of this very long motion. But now if I turn on the events, you see it's no problem. It's getting the same amount of light, but it's still fast. Plenty fast to do machine vision. It's a little more motion blurred, but it's not blurred like the camera frame. That's because of this logarithmic conversion at the front end and the fact that the photoreceptor is actually active. It's an active transimpedance amplifier. And so this brightness change mechanism doesn't suffer from the same motion blurring that integrates for a long time of the exposure time of the frame. Okay, so now let's open up the lens again. You see, when I open and close the lens, it really doesn't do anything at all to the DBS. It just makes them on events or off events, on events or off events. That's like going in and out of the shadow, but it doesn't really change anything except make this background events, right? Because the whole brightness is changing. But if I look at the frames and do that, it becomes totally, let's turn off the events. I close it, open it, becomes dark.
So Toby, I think I saw this demo 20 years ago when your first cameras, when you had sunglasses. And you had something going behind the sunglasses and it looked, it did not dim the events.
Yeah, so I'll do it with the events here. Let's see. So this is pairing a pair of these mirror shades that I got on. They're actually Polaroid sunglasses for $5 from Amazon, because we're actually building a polarization version. We built a polarization version. Yeah, I put the sunglasses in front, and you can see that it looks the same behind the sunglasses. It just sees right through it, right? Because if you think about it, behind the sunglasses, the log intensity change is exactly the same, because the log intensity change reports the reflectance change of the scene. And what's important for vision is how much the scene reflectance changes, not how much light is shining on it. That's the kind of fundamental concept that it only tells you about how the scene reflectance and how objects are moving around. Okay, so I have 2 more demos here. Yes.
So you were mentioning that it only depends on how much the reflectance changes and not how much light is.
If the light is varying, that's a problem, right? If you have flashing light, like the sodium lights or the old LED lights flashing at low frequency, that produces a storm of events from this chip. But normally lighting is not varying. It's constant.
But if you change the exposure, the absolute value of the light that's actually hitting, the delta change in the intensity itself is changed, right? I mean, you will see smaller difference in the delta when you, like if you probably, if you make it darker, then like how is your DBS sensor working even fine in a low exposure scenario?
Do you follow the question? I don't quite understand it.
So you're basically showing that even when you have very little light, you need to wait a lot more time, correct? For exposure when you had a regular camera instead of a TV.
Yeah. If it's dark, you have to expose the frames longer to collect enough electrons to make a readable output voltage.
Yeah, but why is that not a problem in DBS? DBS also.
Yeah, it's because the current to voltage conversion is logarithmic and continuous in time. It's continuously converting it, not integrating it and then reading it out. I mean, it's continuous, it's low pass filtering it still, I'll show you later, but it's continuous time. Right? It's not sample data like a normal camera. Yeah, the DBS pixel kind of samples itself. It's a change driven sampling, right? When the brightness changes enough from the memorized value, then you emit an event. Okay, so let me try this first here. So at my brother's house, I built this little stimulus with this card. If I now take this, let me flip this around. If we're lucky, this works. And I can take this 2 of clubs. You guys can see this? I can spin it, hopefully really fast. Yeah, like that, right? You can't see it anymore, right?
Blur.
It's blurred. Okay, so now let's take the events. I don't mind. I love doing these demos. You guys, I guess you guys can tell that, right? Now, where are my events? And they disappeared. No, I need to turn on the events. Where are they? Okay, they're there. Now I'm gonna make them nice and black and white events. That's easier for you to read. Okay, there it looks like a picture. Okay, so now I'm going to hopefully, Gert, can you come up here, please? I need your help, man. I'm gonna take this, just stand up here and push L. The L is to start recording and L is to stop. When I tell you go, I'm gonna record this. Wait a moment. Is it in focus?
Are you good?
No, it's not in focus at all, man.
I'm not.
I don't trust you, man. I'll move it away a little bit. Yeah, let me, okay, that's better. Now it's in focus. Okay, ready? On, go. Did you record it? Now stop it again. Okay, good. Okay, now I'll save that. I save that. Now I'll play it back. Okay, now here is real time, right? That's a recording, just playing it back. But now because we recorded the address and timestamp of every event, we don't have to play it back, you know, the same frame rate. We can just play as much time as we want. Like we can slow down to, you know, 3 milliseconds or 2 milliseconds. You see the number up there? That's how much time we're showing in each frame. Or 500 microseconds. You can really go slow. Right, like 100 microseconds. You know, it's noisy and stuff, but you know, super slow motion. Basically, you can choose the frame rate you want to analyze it, or not use frames at all. You can just process event by event. Now, is that clear?
Because you have to integrate them. You have to integrate events in your brain, right? To see what's going on.
Why is it so slow now? Something changed here. Oh, I see. I'm running the actual sensor at 1,000 frames a second. Hold on a minute. I have to change this. Oh no, I'm trying to render at 1,000 frames a second on the computer. Okay, that doesn't make any sense. Okay, let me go to 100 hertz or something. Why is it still so slow? I hope I don't have to quit here and restart. Okay, actually, I guess, yeah, something has slowed down dramatically. What's going on here? I don't want that either. Did it die? Okay. Okay, now maybe it's okay. Yeah, something dramatically slowed down. Oh, you know what I'll do? Yeah, there's some, let me reset it. You guys like this, right? If something goes wrong, that's always more interesting. I still remember their very first neural network meeting when the lovely fellow got his electronic music working, his neural network music synthesis. Okay, so now I'm going to show you something quite cool. So everybody knows that we have a vestibular system in our head, right? These semicircular canals, which tell you how your head is rotating. And in fact, that's how you stabilize vision. When you quickly move your head like this, looking at something, it stays very still. But if you try to move the thing, you can't see it, right? So you have this feedback control loop, which has the quickest latency in the whole brain. It's about 6 milliseconds. It stabilizes vision against motion blur, which is very important, not just when you're doing this artificial thing, but anytime you're walking around, your body's actually bouncing dramatically. And so you have this very sophisticated mechanical system that stabilizes vision against rotation and translation. And so the question is, can you do something like this with these event camera? Let me hide this cloning panel, yeah? Okay, so I I realized that this is important, right? Nowadays, because of cell phone technology, you can buy inertial measurement units that are a lot like vestibular systems. They're very cheap, $1 each. They run a few milliwatts. They sample the rotation and the acceleration, or even the compass direction for a milliwatt, nothing, at a kilohertz. They're really, really amazing devices. So can you electronically stabilize this output? Instead of mechanically stabilizing it, which is very expensive, can you electronically stabilize it? And so here is actually the IMU output. Let me show you this. Ignore the green arrow. You see this pink arrow in the middle? That's the rate gyro output. If I rotate the camera, it's telling me how much it's rotating. Let me pause the picture here. No, I can't actually. Oh, I see. It's telling me the camera is rotating to the right at 4 degrees per second, and or something like that. And it also tells me how the camera is rotating along its axis, right? You see how when I rotate it, that top thing? So how can you now take this rate gyro, which is one part of the inertial measurement, is just telling you how the camera is rotating in space. How can you now use that just to electronically stabilize the output? Can you imagine how that works? Remember, each event is an XY address and a time.
So you just shift it.
Yeah, you can just shift it back where it started. So you can integrate this derivative information to get a shift and a rotation and integrate that back. Okay. So if you do that, it's actually quite cool, because if we take the normal output and imagine this is on a walking robot, and now we turn on this so-called Steadicam, which uses this IMU output. Hopefully that works. Yeah, it does this. This is with the IMU Steadicam, and this is without it. You see? It's not perfect because the lens optics changed a little bit. But this is with this electronic stabilization. Yeah, you see it's shifting a little bit. So the somehow I shifted the focal length of the thing. Yeah. And the beautiful thing about this is that because the events are so fast and you adjust it right, you can really reduce motion blur by integrating the very sharp features even under very low lighting. And so that's really useful for robotic vision.
Oh, by the way, is this kind of future kind of open source?
This software?
Yeah, the software and this kind of future algorithm, like using the IMU to deblur the.
Yeah, I mean, this is in a paper, ISCAS paper. You can read about it. In fact, you can just run this directly, and it's all open source code. It's called Steadicam, and this software that we developed. I think many people have it now.
Okay.
Yeah, it's quite straightforward to do it. I mean, you know, the mathematics is very simple. You just have to integrate and then compute a rotation matrix, and each XY event address, you have apply a 2x2 rotation matrix and add one translation vector to it. It's like 6 mathematical operations per event that you have to do to invert this stuff. It's really cheap. You can implement it in hardware, in fact, quite easily. You know, it's just a few logic gates and a couple of multipliers. Okay, so
Can you do that for the image itself, not just the?
yeah, so people do this routinely. For example, you take all the big smartphone companies, Apple in particular, they also use the IMU to try to deblur the output and do all kinds of sophisticated image processing. But imagine it's much more expensive and complicated for an image, because those are analog values. You have to do sophisticated interpolations, all kinds of fancy signal processing, you know, when you're doing it for image stabilization. Much simpler with these events to stabilize it against camera rotation. Now notice we haven't done anything with acceleration yet. You know, we're not even know how to use the camera acceleration in space, because that depends on how far things away are in the scene. The camera rotation is easy to stabilize, but not the acceleration. Okay, the last thing I just want to demo is something quite cool, which is a little game, which I had a lot of fun with over the years. And the question is, I'm sure you all know what Rochambeau is. In fact, I learned what, you guys are all here at UCSD. How many people know what it means when I say Rochambeau?
No, I would do.
Nobody knows? This is the game that I played here as a student here at UCSD. It's like,
How long
who's gonna
ago?
pay for the beer?
How long ago?
Yeah, Rochambeau, rock, scissors, paper. Yeah, you know it, right? Okay, so how, you know the answer, right? You guys all know the answer already. How can I guarantee you right there? How can I guarantee that's you? What's your name in the middle there?
Oh,
Nicholas.
Okay, Nicholas, how can I guarantee every time to beat you at rock, scissors, paper? Guarantee.
With the camera?
If I could watch you in super slow motion, right? If you saw me doing that, then you would keep the rock, right? If you saw me doing that, you would throw the scissors, right? You turn it into a physical sport. Okay, so I show you, I'm not going to show you actually the robot. They don't have the robot, but you can imagine now taking the data from the sensor and just making frames out of it, but very sparse frames. Most of the pixels are 0, and then just setting it into a very tiny CNN, which is trained on label data that identifies what symbol you're showing. It's not a gesture in the sense of having dynamics, it's just which symbol you're showing. And I want to show you that actually running here. Hopefully that works. A Rochambeau CNN. Let me just make one small adjustment here. Did I turn that on? Oh, I see it. It never got actual power. Oh, I see. This thing was never on. Okay. You see, this kind of demo takes a lot of joules, even though the camera is very power efficient. This is a powerful gamer laptop that burns about 50 or 100 watts to run another demo that I had. Okay, so anyway, that's running now. Hopefully that works. Ready? Rock. Scissors. Paper. Let's use the other hand with the watch. Scissors. Paper. If we go further away, make it smaller. Actually, you can barely see the hand. Yeah, so this I think is really beautiful because now you see the compute time of this little CNN is only about a millisecond. That's the actual inference time, about a millisecond on this, laptop GPU. It's a little tiny CNN with about 20 million weights, 20 million operations per frame. The frames are only 64 by 64 pixels, but the key thing is that the frames are activity driven. In other words, each frame is like 2,000 of these brightness change events. You just accumulate them. They have an extremely high sparsity, and you send that into the CNN. The CNN doesn't care about this activation sparsity. It's just a normal, dumb, industry standard CNN. It computes all the pixels, even if they're 0. But the frame rate depends on how fast I move. Because if I move my hand really fast, I get 2,000 events faster, right? So that's the key thing, right? And I'll show you actually, I hope it's here. Yeah, here are the input frames to the CNN, and hopefully this works. Oh no, it's not showing the frames. That's the wrong one. It did show the input frames. Hopefully that works. Okay, here we go. So if I move my hand very, very slow, you see the frames are updating slowly. But if I move my hand really fast, it updates really fast. And that way you don't get any motion blur. The faster I move my hand, the faster you get this frame. And so you decrease the integration time, just because you're counting a constant amount of change. It's a very simple idea. Doesn't always work, right? In this simple application. So you can come and try it if you want. But this is just standard Lynette architecture from Jan LeCun, trained on labeled data from about 20 people. Collected, each person 2 minutes of this, 2 minutes with this hand, rock, 2 minutes scissors, millions and millions and millions of frames, all the dumb backprop and so on. And at the end, after all this data, it really just works. But it demonstrates the idea of this activity-driven computing.
No, why a CNN? Why a continent? Why not a neural network or an event-driven?
Yeah, that's what we did actually. We developed an accelerator called NullHop, which exploits activation sparsity. It's a CNN accelerator. It exploits activation. It only computes the neurons that are active, that are spiking. But this is running on a standard GPU, so there's no point to do that. You can't exploit it. Okay, so that's it. I hope it was a little bit of a core dump, and I hope you enjoyed this history of the silicon retina technology and this live demo. And then we'll take a break, and then maybe I'll do some Blackboard stuff for the students. Okay, thank you.
Want to move forward with the.
It's quite long already.
Yeah, I might as well do the whiteboard now.
Yeah.
People are welcome to go.
That was pretty long actually.
Yes. Where? It's not. Yeah.
Because like, whatever you feel.
I just want to know the name.
It's right now, it's 5.
So watch it. The name of the software is just.
It's J-R.
Okay.
Oh,
This is J-A-R. This is my
Oh, yeah.
software, but I wouldn't use it. It's
Very
kind of
interesting. What are the plans for tomorrow? Do you want to have a business lunch? Yes. Okay, we'll be finished up at some point.
We're out of finances.
That was great. No, we're having dinner. But you're gonna get some good afternoon.
Let me just show you here. Imagine that you wanted to turn the light photocurrent into voltage logarithmically. One way you can do it, and that's the original way, is to build a pure logarithmic photoreceptor just by putting a transistor up there and converting the current into voltage using the exponential IV relationship of this transistor, right? You just set this voltage here, this gate, to a constant voltage, and then you get the log coming out here, right? Because the current is exponential in this VGS, so the voltage is logarithmic in the current, correct?
Is it because it's in subthreshold?
Yeah, you assume this is subthreshold because usual photocurrents are very tiny. Biggest photocurrent you're going to see is a nanoamp or so, right?
Sorry, could you help change the screen so that we can see what is in it? Thank you.
Is it still sharing the screen?
Oh, yes, unshare screen. Please.
Yeah. Now, can you share it? Unshare it?
No, just unshare your screen and look at it.
How do I do that? I hid the meeting controls, so I can't no longer unshare. Yeah, you unshare me because you're in charge, right? You're the
Oh, I
boss.
see.
Is it done? Or I just leave? No, I can't leave the meeting. Oh yeah, I can leave the
Stop
meeting.
sharing.
Oh yeah, okay, good. That's good.
Are we good now?
Yeah, it's all good? Okay, good.
All good.
Now, can you see actually this screen? I'm probably not drawing it big enough. Yeah, so but that's not how we actually do it because it turns out that that's much too slow. Because the very fundamental fact that you learned already in this course, that every time you have a photodiode, you also have capacitance, parasitic photodiode capacitance, right? And if this is a fixed voltage here, just call it VDD for convenience, then this output voltage here, which is the output of this logarithmic photoreceptor, what's the time constant or the rise time of this thing set by? It's set by the RC time constant, right? What's the R? It's just the source conductance of this FET up here. And this source conductance G is just proportional, since you know the course. If this current is I, what's the source conductance? Yeah, I over UT, right? UT is the thermal voltage. It's as simple as that. That's the most basic thing about subthreshold. So this time constant here, tau equals C over G, and you can see it works out that it's CUT over I. That works out too. CUT is a charge, CB, right? That's charge, divided by charge per unit time is time. Okay, so that's the basic time constant passive thing.
You use the voltage, right?
Yeah, it's the voltage.
UT is like
Okay,
a
okay,
V.
okay.
Yeah, this is output voltage here, which we call VP, D. We'll call it VD because it's the diode here. Okay, the problem is that this becomes very weak at low light intensity because the smaller the current, the smaller the current, the smaller the conductance. Becomes extremely weak. You can't drive something. So what do you do about that? How can you make it faster and drive something? You have to amplify it somehow. You could just put a buffer on here, right? But that wouldn't help it make it faster. It would also get, the darker it gets, the slower it gets. So what do? So the very simple trick, you turn this into a transimpedance amplifier. You put an inverting amplifier here, which just is 2 transistors. You know, there's a current source up here. And then there's an NFET here. And then you just tie it like this. Instead of tying this to a constant voltage, you tie this gate to the output of this amplifier. Now, let's reason how that works. First of all, it's negative feedback, right? Because if this VD goes down, then what happens to VP? Goes up, right? Okay, so suppose this current here increases a bit. What happens to this VD? If this current increases, more current is pulled out, so this VD goes down a bit. What happens to VP? Goes up a lot, 100 times as much, because it's a voltage amplifier, right? Okay, and that's the gate of this transistor. So this is really cool, very simple idea that now instead of the source going down, the gate goes up. And also you can make this current as big as you want. So you can make this really strong. You can drive anything you want. And the coolest thing about it is that, and this is the coolest way to think about this, is that what does that do to the effective source conductance of this NFET? When I pull down on the source and the gate moves up, it's like the source conductance gets bigger. It amplifies the source conductance. If it amplifies the source conductance, makes this bigger, it reduces the time constant. It's like making it quicker. And so the tau in this feedback loop is divided by the voltage gain here, A, which is, D VP dVd is defined as minus A, right? It's an inverting amplifier. So that reduces the time constant by a factor of the voltage gain. Makes it A times faster. You can make it 100 times faster, except for one very important thing, which in practice actually starts to dominate, which are these things called Miller caps. Do you guys know all these Miller caps? Yeah, there's a Miller cap right here, which is the traditional one. And there's also one right here, which is not usually talked about. And when you now think about it, this little Miller cap also gets amplified by this voltage gain, because now I'm trying to drive this node down a little bit, but if the other side of this cap goes up in the opposite direction, you have to charge that, not the CM, you have to charge A times CM, to get it to the final voltage. So, but still you can get speed up, right? You can put a cascode there. You can't do much about this Miller cap. Okay, so that's the first thing. That's basically how all these DVS photoreceptors work. They're just transimpedance, logarithmic transimpedance amplifier. This thing is usually a big voltage, like 3 volts. And we really should run this amplifier quite hard because you don't want much. We want to spread the shot noise over a really big bandwidth. Now, what's the next thing you've got to do? Yeah.
You're now, this feedback loop is basically desensitizing it to variation in the current. I correct?
Yeah, okay.
But
I should
can
actually
also change the gain for any, if we want to detect the delta I, wouldn't that also, the gain also reduce?
basically, let me just show you how this works here. First of all, this is just except for the dark current, when the current is really small, this just has a linear response like this on a log scale. It's just a logarithmic thing until you go above threshold, and then it kind of increases actually. But anyway, we never get up there, just like that. And because this, this power supply is like 3 volts, we always use a big power supply. It covers about 6 decades of dynamic range.
Yes. Color, yes.
Yeah, this should go in the trash.
Something darker.
This is anti-social pen. Okay, anyway, yeah, so did that answer the question?
I was basically asking, wouldn't this feedback loop also affect the gain, the sensitivity for the changes in the current? Like,
only DC,
yeah.
right?
No, it won't affect the gain. As long as the gain here is big enough, it totally doesn't. It only depends on this slope here. And in fact, this slope, you can work out, it's extremely simple. This slope is exactly, it's in volts per log intensity, volts per E-fold. What do you think it is? Remember, it's the gate of an NFET. Volts per E-fold. You guys who have the intuition, the VD here stays clamped, right? That's the beautiful thing about this feedback. Instead of going down, it actually stays almost constant. So what do you think the slope is? Yeah. UT, thermal voltage over kappa. Kappa is the back gate coefficient of that FET.
And now this will confuse everyone in the class here, because we had another case where the kappa was in front of the voltage, but that was for source follow output.
Yeah, okay. Now it turns out that it's very important to follow this by some kind of a low pass filter, because this thing has a lot of bandwidth, and if you have low light intensity and a lot of bandwidth, it gets extremely noisy because the integration time, the time window over which you're looking at photons becomes very short. And if the light is dim and you're looking over a very short time, you have lots of fluctuations in the number of photons that you're collecting per unit time. And so you have to put a low pass filter after this. Typically, we just put a source follower here. We just put a source follower. Except that it's drawing it badly here. We'll just put a current source up here. That's a P-type source follower, right? By the way, I really like this Andre von Schaik. You don't bother, you just draw a line. The transistors are simpler. Yeah. So this is a P-type source follower, right? So this VSF follows VP, right? If this goes down, this VSF goes down, because basically this transistor always has to have this ISF bias current flowing through it, right? So if the gate goes down, the source has to go down too, but with a slope of kappa. Right? Now you have UT over kappa here, but here, this thing has a gain of kappa, right?
As we learned in the midterm.
Yeah, the gain is less than 1. The gain over there is less. So now you have a gain here of UT per E fold. You got rid of the kappa. Those two kappas kind of cancel each other. Really simple.
Well, if you assume the kappa for the PMOS is the same as the kappa for the
Yeah, but it's almost the same. It's close enough. Yeah, close enough for this analysis. You have a ratio of the two kappas, but basically they almost cancel. Yes.
Question here. So if you're in the photodiode, right, if the current changes quite significantly, increases quite significantly, the capacitor would, the voltage would go down significantly, right? There.
Yeah, if you have a big step of photocurrent.
Yeah.
Big step, right?
So this is good for low lighting, but like if there's like
small signal.
Small signal, I see. But
Yeah.
if there's like a lot of light in the room, would this still not cause a lot of light?
You were asking, does this transistor go above threshold? Yeah, it can if the sun is shining on it. Yeah.
Well, even
Or like
then,
just
no.
like a lot of light, right?
You know, it's possible when you really go above threshold, you know, the gain actually gets steeper, right? Because it takes more gate voltage to change the current. So actually, this curve actually gets steeper, not flatter. It's the opposite of the normal transistor curve, right?
Yeah.
That does some weird stuff. Let's not worry about that. That's all second order. Okay, so that's all nice. Now, what we can do with this current here is we can low pass filter this, and we can take that huge amount of noise and just filter it away again. We spread the noise over a big bandwidth, and then we just chop out the part that we care about with a low pass filter. We might only care about up to 1 kilohertz or 100 hertz or something, or even 5 hertz, right? Depends on the application. Okay, so now we have to make these change events. You guys ever seen a switch cap circuit? Yeah, okay, so let me show you what I think is a really beautiful circuit. This is the change detector using these DVS pixels. Which turns out to be so simple and so beautiful and so symmetric. I just love this circuit because it's so simple. You can detect, you can amplify by a factor of A and detect these changes with 7 transistors, 1 switch and 6 transistors. That's it. Do you see how it might be possible? It took us a while to come up with it. It's dead simple though. I'll draw you the circuit. You have 1 big capacitor, C1. Then you have a PFET. Down here is a current source, which is a FET. We call this ID for differentiator. And then we have a feedback capacitor here, C2, and 1 little PFET switch. That's the reset. So we have C1 there, C2. You know, this is just 2 transistors, right? Okay, so what happens if I short this PFET? I turn on this PFET, what happens to this transistor up here? It becomes diode connected, right? It's a diode connected PFET. If I connect this switch here, forget about the capacitor, all it does is diode connect this transistor, right? That means that the gate voltage will settle down to where this PFET sources this ID. Simple as that, right? Now I disconnect the PFET. Now, this is just another voltage amplifier, right? If this voltage goes down because this goes down, if this gate voltage goes down, the output goes up 100 times as much, gain of 100, right? Okay. Here's how this switch capacitor voltage amplifier actually works. It's so dead simple. You don't need any mathematics at all. Because of this negative feedback loop, after I disconnect the switch, this voltage here is clamped at whatever this diode connected voltage is. So now suppose that I have a delta VSF here. How much charge does that put onto this node? right, across that capacitor, yeah, it's C1 delta VSF, it's put onto the capacitor, onto this node, right? Through this through this C1, it's CV, Q equals CV, right? If we're gonna keep this voltage here constant, we have to take the same charge off the other side, right? How do we take that charge off? That has to be true. It has to be equal to minus C2 times delta VD. This is VD here. You see that, right? The gain is just C1 over C2. That's it's as simple as that. One line, not even a line. So delta VD over delta VSF was minus C1 over C2. What could be simpler than that? Yeah. It's beautiful. It's just charge equality. And so it's easy to design, you know, I mean, there's always some limit, but you can easily design a ratio of 10 to 1 by using unit caps, or you don't even worry about unit caps. You just care that it's some ratio. So you just draw a big cap and a little one next to it. You know, and it's very well matched, pixel to pixel. The capacitors match very well, like better than 1%, even with minimum size caps, because nothing matches better than caps, right? Nothing. And so then you have this very well-controlled voltage gain here through this change amplifier. And now how do you make a threshold on that to detect whether you get an on and off event? It's dead simple. You just take this voltage here, which after all is the output of this amplifier, and set it into 2 MOSFETs. And 2 different currents down here, which are a little bit bigger than ID or smaller than ID, which we call I on and I off. So look what happens in reset. I on is less than ID and I off is bigger than ID. Hope you can read my writing there. Suppose ion is bigger than ID. That means when this thing is reset, this transistor is trying to source ID, right? Because in reset, this is direct connected. And so this PFET is sourcing the same current as this one. It's the same voltage, right? So it's trying to source ID, but ion is bigger. So therefore, this voltage sits low after reset. But this voltage here, I off, is smaller than this current. So this one sits high. Now, if there's a change of intensity, which say increases the light intensity, if this goes up, this goes down, it turns this on, and then if there's an event, an on event, this will go up to VDD. Likewise, if there's a change in the other direction, this will go down. Those are the on and off events. It's quite cool, right? It's just 7 transistors. 2, 4, 6, 7, and 2 caps. You get all the function in a very compact area. Now, it helps to make these FETs big, right? Because that improves the matching. And maybe we should stop here. That's the basic idea. I just want to show you one more thing, which is really cool, which we only discovered like maybe 3 years ago, which is how does this thing change with temperature? How does the threshold change with temperature? And look, this voltage here is proportional to temperature, right? That's UT. But it turns out that this threshold is inversely proportional to temperature. And in fact, the voltage threshold here of this change detector goes like 1 over UT. And so those cancel out. So it turns out that this brightness change, log intensity change theta, which we call theta, for on events is actually almost equal to the natural log of the ratio of the currents, like the theta on. The on threshold, the amount of log intensity change to make an on event is almost exactly, it's like 1 over kappa, like there's 1 over kappa, times the natural log of the ratio of these 2 currents. it only depends on the ratio of these currents, totally independent. As long as you can make a ratio of currents that's independent of temperature, then the threshold is temperature independent. And it's just an accident. We didn't design it that way. It just happens to work out because of the beautiful physics of subthreshold transistors. In fact, we didn't even compute the threshold from the current until about 15 years after we designed the pixel. We thought it'd be really hard, but it turns out to be dead simple to compute the threshold. So, you know, we were lazy, didn't actually do the basic analysis, which is really only a few lines of mathematics. For about 15 years, we just adjusted stuff by hand. Yeah, so maybe this is enough for today, because it's a lot of stuff, but it's enough just for discussing, right? It's fun. I never mind talking about it. Great. But it's probably a bit much.
More questions?
So this operating in low frequency, do you see the severe effect from the flicker noise?
Yeah, flicker noise is never important, it turns out. What's always important is the shot noise. The shot noise, which is the quantal flow of electrons and photons. The flicker noise is never important here. We can't even measure it. It's so dominant under low light intensity. The only time this noise really matters under low light intensity. The low light intensity is totally dominated by this shot noise current and this shot noise, and also in these two transistors if you run them at low current. And that's why it turns out to be, if you really want to get the best noise performance, you have to crank this guy on hard and then low pass filter it afterwards to control the bandwidth. Basically push the noise out to high bandwidth and then average it over time.
Yeah, it's a myth that subthreshold circuits are very noisy. Well, they are, but
they're basically electron shot noise limited, right? If you operate them properly, there's no excess. I mean, I know there's flicker noise, right? That depends on some applications a lot.
But not here, because the current's so low that flicker noise.
Yeah, the current's that's right. The current's low and it's totally dominated by just the quantized flow of electrons. Yeah, not by this flicker noise, which caused by the carriers in the channel tunneling into the oxide and acting like boulders in the stream. You know, this flicker noise is caused by this tunneling of the electrons into the oxide and tunneling back out. And when they get stuck in the oxide like that, they tunnel at various rates. Each has a time scale and causes this flicker noise. This tunneling in and out of the oxide is like boulders getting stuck in the stream, blocking the flow. That's the fundamental mechanism of flicker noise. At least I believe that's the mechanism. So tunneling into the gate.
In fact, the classic paper on subthreshold noise in transistors, not one flicker, but then the thermal versus shot noise, the improvements between the two, was written by Tobi.
No, but the person who really figured this stuff out was Rockwood. I just was obsessed by the idea that you could actually understand the noise in these logarithmic flow receptors, and there was this factor of 2 that just drove me crazy. I couldn't figure out. I measured very, very carefully the noise spectrum, the absolute value. I couldn't understand why it was 2 times bigger than I thought it should be. I finally figured out the theory why it's exactly, the noise totally consists of this shot noise plus the shot noise of the current, current flowing from the source of the transistor. Those 2 shot noises add up. This whole GM, you know, this whole resistive noise is not the right way to think about it for subthreshold. It's really just the root M noise of counting electrons. You know, how shot noise works, just counting noise, basically. Yeah.
It's a beautiful paper. Was it IEEE micro?
Yeah, I don't know right now. Anyway, that's enough for today. You guys, there's a lot of stuff. You guys are probably exhausted completely.
Great.
Yeah.
Thank you very much. We keep going for many more hours.
That's fun.
Hello.